Pluto is a distant and stealthy, more unpretentious planet that was once a part of our nearby planetary system. However, advancing and disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back to the forefront of attention. They propose that this chilly world is on a potential collision course with Neptune. But how could this really work? And what might be the results of such an enormous event? Are we seeing a bewildering, huge erraticism? Or is there something else to this looming, unending setback? Join us as we take a closer look at the potential consequences of Pluto's orbit. Pluto, former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the vast universe. As suggested by recent hypotheses from leading specialists, Pluto's orbit is perilously close to Neptune's, and astrophysicists Neil deGrasse Tyson, Michio Kaku, and others are raising the alarm about a potentially hazardous accident between these two bodies, which could represent a massive risk to Earth. But how is such an event even possible? Pluto's trip around the Sun is unlike that of any other planet in our solar system. It requires a dazzling 248 years to complete one orbit. Since its discovery in 1930, it hasn't even finished one full revolution. The interest doesn't stop there. Pluto's orbit is marked by its particularly elliptical shape, wandering widely from the almost circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, which is 17 to the ecliptic plane. The way Pluto follows its path is significantly more disorganized than that of other planets. This tendency and unpredictability add layers of complexity to its orbital arrangement. Potentially one of the most intriguing parts of Pluto's orbit is its intersection with Neptune's, for about 20 years in each orbit. Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This prompts the usual question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. Shortly after Pluto's discovery, astronomers began examining its orbit. Initially, they attempted to figure out its unique path. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's orbit stands out with its deep inclination and erratic shape. The mystery grew with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these intricacies, is evidence of the complexities of three-body mechanics. The three-body problem in space involves determining how three objects like Pluto, Neptune, and the Sun move and influence each other. Gravity makes it seem like trying to predict where they will go based on where they started and how they pull on one another. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. Terms like non-concurrent libration, orbital precession, and VZK wobbling are key to this puzzle, or as explained by astrophysicists. What keeps all planets in their orbits is non-concurrent libration. In regard to Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is positioned no less than 90 away from Neptune. This spatial separation is critical in preventing their orbits from intersecting dangerously. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential impacts. Another important aspect of this situation is VZK, wobbling, named after the three researchers Volk, Joe, and Kaku, who studied how objects move in space. It involves how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling influences how they move. In Pluto's case, us. The VZK wobbling helps us understand why its orbit, especially when close to the Sun, is so unusual. Despite the chaotic appearance of Pluto's orbit, this wobbling helps keep it moving smoothly over extended periods. VZK wobbling shows that although things in space may seem wild and unpredictable, patterns and rules maintain some control. These forces help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or drift off course. This three-body problem is crucial in understanding how these orbits change because of how space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and even distant worlds and their stars. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is actually erratic with minor differences in the initial conditions leading to huge changes over centuries. However, these peculiarities of Pluto's orbit have been found to maintain stability over extremely long time scales. Later automated examinations helped us understand how massive planets such as Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonant relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet at work. Jupiter's gravity also plays a colossal role in stabilizing Pluto's trajectory. The same goes for Saturn. Studies show that Jupiter's massive gravity is strong enough to ensure Pluto stays on a steady path for a long time, potentially even for millions of years. So, perhaps Neptune, Jupiter, Saturn are cooperating to allow Pluto to continue moving safely through space without running into trouble. These idiosyncrasies are key to keeping everything in place and safe in space. Without these mechanisms, the solar system as we know it would be a much more violent place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future understanding, its orbit is crucial. This provides a clearer picture of the dynamic nature of our nearby planetary system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also underscores the importance of constant observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies and Pluto's orbit is an excellent illustration of this irregularity. The idea of orbital chaos refers to the fragile dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can dramatically alter its long-term orbit. Using automated simulations, it's been hugely helpful for scientists in figuring out how Pluto moves through space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on each other by tweaking small details in the simulations. Space researchers can see how even minuscule changes can make a huge difference in where Pluto ends up in the late 1980s. These simulations showed something interesting about Pluto's orbit. Despite having features like asynchronous, libration, and orbital precession to keep it stable, its orbit can still be inconsistent and unusual. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. Yet despite this chaos, Pluto's orbit remains stable over vast timescales, like billions of years. This means that Pluto's journey around the Sun has a kind of order to it, even though it initially appears wild. Predicting celestial movements, particularly when they involve irregular orbits like Pluto's, is a massive challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While numerical models provide excellent tools for understanding and predicting the future movements of celestial bodies, they also highlight the limits of our predictive abilities. These models heavily depend on the accuracy of initial conditions, and any small mistake or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Other than the chaotic nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us of how much our knowledge of the universe still remains limited. Grasping the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and course of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces trying to prevent such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and a major figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, especially the intriguing case of Pluto. Tyson, known for his role in changing Pluto's designation from planet to dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's interest in the neglected corners of space. Tyson's position on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He doesn't see the renaming as a diminishment, but as a necessary adjustment to our growing understanding of the various bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The interest in these questions keeps the study of space so exciting, however. Despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the fate of Pluto's orbit rest on a simple truth. As the solar system continues to evolve, the gravitational dynamics between bodies like Pluto and Neptune can subtly shift over time. Even though the probability of an immediate collision is extremely low, Tyson and others in the field cautioned that it could happen over billions of years. Should the gravitational forces between Pluto and Neptune ever become unpredictable or unstable due to small shifts, the entire system could go into chaos. Among Tyson and other astrophysicists, there is acknowledgement that while the current dynamics between Pluto and Neptune seem stable, we must consider the long-term implications of their orbits. Over billions of years, even the smallest changes in gravitational forces could alter the balance that keeps them from colliding. It's a stark reminder of the unpredictable nature of space and the vast time scales involved. The possibility of such a collision, though exceedingly rare, is a theoretical concern that highlights the fragility of celestial mechanics in our solar system. Neil deGrasse Tyson's comments also bring into focus the broader issue of how the solar system is constantly evolving. With every orbit and every gravitational interaction, subtle changes accumulate. In the case of Pluto and Neptune, while their current orbits are synchronized in a way that prevents direct collisions, there's always the possibility that over immense timescales, this delicate equilibrium could alter. The fact that Pluto's orbit intersects Neptune's for a portion of each orbit adds an element of vulnerability, one that, though highly stable now, could be susceptible to change under the right conditions. Moreover, there's a long-term gravitational tug-of-war at play involving not only Neptune but also other large planets like Jupiter and Saturn. These massive giants exert their gravitational influence on Pluto. And while this influence helps stabilize its orbit, it also means that Pluto's path is in constant motion. Small adjustments to the planet's orbits around these massive stars could, over millions or billions of years, shift the gravitational forces enough to make Pluto's orbit unstable by position. In this sense, Pluto's orbit can be viewed as a dynamic, shifting puzzle where all the pieces must fit just right for the dwarf planet to avoid any potential catastrophes. Yet despite the potential for change, it's important to remember that our understanding of the solar system is still evolving. As technology advances, new models and simulations offer deeper insights into the long-term stability of planetary orbits. Future observations could reveal even more about how planets interact over time. It's further refining our predictions and perhaps even providing new solutions to these cosmic puzzles. The case of Pluto and Neptune serves as a valuable reminder that while space may appear vast and infinite, it is actually a place of constant motion, change, and unforeseen possibilities. In conclusion, despite the possibility of Pluto colliding with Neptune seeming far-fetched and improbable in the immediate future, the study of their orbits provides a fascinating look at the nature of our solar system. The intricate gravitational relationships between planets and dwarf planets like Pluto showcase the delicate balance that exists in space, where even the smallest changes can have profound effects over time. Astrophysicists like Tyson continue to investigate these mysteries, which remind us that the universe is far from static and our understanding of it is ever evolving. As we look to the future, it's clear that space research will continue to be a rich field of discovery, where surprises, mysteries, and new revelations await.